Hi, my name's Margaret Franzen. I'm from the Milwaukee School of Engineering Center for BioMolecular Modeling, and this is my colleague.
I'm Cassidy Terrell. I'm from the University of Minnesota Rochester.
We have a lot of fun together on the CREST grant. CREST stands for Connecting Researchers, Educators, and Students. It's an NSF-funded project, and part of the project allows us to work with educators to develop hands-on materials to teach concepts in their class. So Cassidy, you've got a new model here to tell us about.
So this is part of a series of models that I use in the enzymes content of my undergraduate biochemistry course. My course is flipped, so the students will watch a video outside of class on the content, answer a few questions, and then come to class to work in groups to try and again get at the same content in a different way. And so the first day of enzymes, which goes with this model, is about enzyme substrate binding. So haven't gotten to catalysis yet, haven't gotten to much of the transition state. It's more about how do enzymes bring the substrates in the right orientation and proximity for catalysis. And this particular model set is meant to be relatively simple compared to the series that they'll see next, which kind of get progressively more advanced. And the example that I have for this are the substrates for hexokinase. So students in the pre-class assignment are given the chemical equation for the reaction catalyzed by hexokinase, which is glucose and ATP. Hexokinase is written over the arrow, and there's also a magnesium written over the arrow. And so essentially what students are asked to do in class is to first take these two substrates and put them in the best orientation and proximity. And I usually also have to start out talking about like what are the renderings here, what are we looking at. So we're looking at the spheres form of glucose and ATP, showing the electron density, the size of the atoms. The colors are in CPK coloring, which my students will have been familiar with from previous visualization activities. And I also note that there are some magnetic pieces to show the movement of the phosphate. So they're able to kind of be like, okay, we can move some of these pieces around and form the products that match their chemical equation.
So my guess is that if you want, let's put it back in the substrate.
Yep. So the first question is just asking them to put these two substrates in the right orientation for catalysis.
So I want these two close together. Do these oxygens interact with these nitrogens?
I don't know.
They might.
Do they?
Well, they could.
They could.
But this certainly has to be close to here for that swap to occur.
Exactly. So the right orientation is to get this oxygen near that phosphate. And so you actually did something that most of the students won't do. Most of my students will line it up in this sort of fashion here, because that's exactly how they see it in the chemical equation, is everything is lined up in a line. So they do have good orientation. I ask them to show me what bad orientation means, and it's just really getting these two as far away from each other, or the atoms not lined up. And then the next is to show the best proximity. So enzyme active sites are not typically extremely large, they're small, and they bring the substrates together in the closest proximity to each other as possible.
I kind of like that.
Exactly. So now you have a good example of orientation and proximity. And that gets the students to think about not just lining things up in a straight line, but how to bring these things close. And then we usually have a discussion about the magnesium ion and where best to place that. So,
and the magnesium is positively charged. Mm-hmm. The phosphate groups are negatively charged.
Yes.
So you want it somewhere over here.
Yep, and magnesium can coordinate two negative charges, so two different phosphate groups.
So I wonder if it's going to do the first and the second because this is coming off, or if it's going to do the second and third to help it to come off.
Exactly, to help it come off.
Okay, so then we're going to put it, we've got a rolly table.
Yes.
So there we go.
Awesome. So this actually takes students a surprisingly large amount of time to get to here, but the piece that we layer on top of this is right now there's no enzyme present. So what I usually have them do is I have a big piece of white paper for them to draw on. These are placed in the middle, And then I ask them to just design an active site that would best bind these two pieces as you see them in the best orientation and proximity.
So then I would probably put some negative charges to hold this.
Okay.
The
So what kind of
The
amino acids
admin.
would you pick?
negative charges, I would probably put aspartic acid or glutamic acid
Okay.
here. Because these are negative charges, I might put some arginines and loose lysines here.
Okay.
I'd probably put some more positive charges over here, arginines and lysines.
Okay.
This is might be a little hydrophobic.
Okay.
I don't really understand pi-cation interactions or ring structures. Should I have anything for a ring in there?
Yeah, you could probably do some sort of pi stacking interaction. So if you had
Okay.
like a phenylalanine or a tyrosine here. So there's one piece that you haven't connected to.
Holding the magnesium in?
Haven't held the exactly. So something that also holds the magnesium
what
in
holds
place.
magnesium in place? Magnesium is positively charged, and it can hold a bunch of things. So it could
Mhm.
hold these two plus maybe two more.
Yeah. So
So any negative charge here to hold the rest of the magnesium in place.
right, and then we just have kind of a conversation about, well, okay, so you put a bunch of positive charges here, a bunch of negative charges here. Like, what if these actually weren't in the active site? What would it mean to have so many positive charges all in one spot?
Ooh, that wouldn't be so good.
Might have like repulsive effects, so it might have impact folding. So then that also gets them to think about like a variety of things. So you picked the strongest interactions that you could. We could throw some hydrogen bonds in there, some more hydrophobic interactions, some things that wouldn't have so much charge
Gotcha.
when the substrates weren't bound. But one thing that I actually think was probably the most interesting thing about using these anecdotally is that when I asked students to create an active site for this enzyme, most of them will only create an active site that binds glucose and will completely ignore ATP. And I find the same thing if you have an NADH or any molecule that is represented by an acronym, they will almost always ignore it as part of something that needs to enter the active site to facilitate the mechanism. So this really helps them understand that both of these are substrates, because
Wow.
both of them are chemically altered in the course of the reaction, and they both have to be in the active site in order to get the phosphate transfer. Another thing, so if we get there, which we usually do, another thing is that, okay, we'll design the active site now. Again, they will stabilize only one of the molecules over the other. So they won't have an active site that will bind both. They'll have an active site that binds one. Or like you may have missed the magnesium stabilization part.
Right.
So that's a really interesting discussions that you can have with this type of molecule that's a little bit more simple. One semester I did bring in the amino acid starter kit side chains, just to be like, let's just place these around here. The size and scale is a little bit off for that. Plus it just added too many more extra pieces. So for me, it was easier to keep this more simple, white piece of paper, just the substrates, let's just draw.
And you can quickly see what they're thinking when they draw it out.
Exactly. And then when they move into their homework assignment, I actually have them use the same thing, but to propose a transition state for this. And like, what would it mean if the enzymes preferentially bound the transition state? What would you change about your active site to represent that? So, and then that leads into the next day of enzymes content. So there's like there's a lot you can do with just a really simple model of two molecule pieces without even having the enzyme represented here.
But this is much easier, I would think, than having them just draw it out, because they can actually
Move things
move
around.
and see where things might fit together.
Exactly.
And for a student like me who doesn't like to write, that would be really handy. And then do they just put like a 3-letter amino acid abbreviation, or do you have them draw out the structures? Or
It depends on how well you write your activity. If you don't say draw the structures, they will just write the letters or the 1-letter codes, 3-letter, 1-letter codes. I've moved to having them draw it because I want to see where they're putting the interactions. I want to see them draw it and label, like, this is a salt bridge. this is
Okay.
an ion dipole, this is the hydrogen bond, and so on and so forth, because I like to make those connections, those electronics connections with content that we've started with in the beginning of the semester. So, but again, it's kind of up to you as an instructor.
That's really good though,
What's
because
important
you're
for
really
you.
getting them to practice with all levels of biochemistry and not just these are the amino acids.
Exactly.
Great.
Yeah.
Thank you.
That's it.